I think now, welcome to everybody, and welcome back to the ones that attended yesterday. And we are QubiTO. I'm Leonardo. Here with me, there is Mark. And welcome to QubiTO Quantum Days, day 2. And
okay. So let's do a brief recap of where we are in this very little event. So yesterday we started with the historic, with more theoretical introduction with Professor Riccardo Adami, who gave us some insights into the most not trivial and interesting points of the history of quantum mechanics. And now we are finally able to go a bit more close to home, if we can say like that, because we are quantum engineers. So we do lots of quantum engineer stuff, like quantum computing. So we are very happy to be able to have this evening of the truth about quantum computing. Thanks also to Professor Scott Aaronson, who is here with us. But I won't do the introduction tonight. I will leave it to the perfect candidate for that, my homie and other QubiTO member, Antonio Pio Sanseverino.
Hi guys, can you hear me? Yeah, I think yeah. Okay, I am Antonio Pio. I'm part of the board of QubiTO. Today I'm really glad to be here because you have one of the most important researchers in the quantum computing community. He is in the computer scientific part, I mean, he's in the algorithmic part. His branch is quantum complexity theory. He will talk more about that. He also worked in OpenAI, and so he's a computer scientist with a big C. Please do a big round of applause for him, Scott Aaronson from OT Austin.
Okay, thanks so much. It's an honor to be invited here to speak at the QubiTO Quantum Days. So, this is a little bit of a silly title, but I want to just give a little spiel, and then I'll be happy to take questions. So, it sounds like you've been hearing for the past day or so about quantum mechanics. But of course, to explain what a quantum computer is, one first has to say something about what is quantum mechanics. So, from my point of view, coming from the computer science, rather than the physics side of this field, quantum mechanics is a certain generalization of the rules of probability themselves. Okay, so we generalize probability to sort of a new way of calculating the probability that an event will happen, where we say that probability is the squared absolute value of a different kind of number called an amplitude. Okay, and amplitudes, crucially, can be positive or negative. In fact, they can be complex numbers. Okay, so you would never talk about a negative 30% chance of rain, but you absolutely can have a minus 0.3 amplitude for some event to happen. Okay, and then the key is that if some event, like for example a photon, this is how I draw a photon here, can hit a certain spot in a screen in two different ways by traveling through two different slits, then you have to add up the amplitudes for all the different ways that event could have happened. And if one of the contributions was positive and the other one was negative, then the two contributions could interfere destructively, as we say, and cancel each other out, with the result being that the total amplitude will be 0. And so then that event will never happen at all. Okay, but now if you block one of the two slits, then now you only have the positive contribution, or you only have the negative contribution, and so now you get a non-zero amplitude, which means that event can happen. Okay, so to summarize, by decreasing the number of paths that a particle could take to reach a certain point, I can increase the chance that it gets to that point. Okay, that's the signature that I'm dealing not just with some detail about physics, but with an actual change to the rules of probability themselves. Okay, namely the replacement of classical probability by quantum probability, or as we call it, quantum mechanics. Okay, so a little bit more formally, the basic building block of a quantum computer is called the quantum bit, or a qubit, which is just the natural quantum generalization of a bit. Okay, a bit is just some physical system that can be in two distinguishable states that we label by 0 and 1. Okay, and a qubit is just an object that can have an amplitude for being 0 and an amplitude for being 1. Okay, so mathematically we write a qubit as a linear combination of the two basis vectors, 0 and 1, which I'm here writing using the Dirac-Ket notation. So I write it as alpha 0 plus beta 1, where alpha and beta are these complex numbers called amplitudes. Okay, they satisfy a normalization rule. Absolute square of alpha plus absolute square of beta is equal to 1. Okay, and now if you measure the qubit, then you force it to decide which one it wants to be. Okay, and it will choose to be 0 with probability absolute value of alpha squared. It'll choose to be 1 with probability absolute value of beta squared. And whichever choice it makes, it will then stick with it. Okay, so if it decided it was 0 and you look again, nothing else having happened, then it will still say that it's 0. Okay, all the other information about the amplitudes has now vanished because you made a measurement, because you forced it to collapse to one or the other. Okay, now I hasten to say, it doesn't have to be a person who's looking. It doesn't even have to be any living organism. Okay, any interaction between the qubit and its external environment that carries away information about whether that qubit is a 0 or a 1 will have the same effect on the qubit as if someone had measured it. Okay, so that will also collapse the state of the qubit from the perspective of someone who only looks at the qubit. Okay, but if you're able to keep a qubit extremely well isolated from its environment, from everything else in the universe, then these amplitudes will evolve in time by their own rules, different from the rules of classical probability. In particular, they'll undergo some sort of linear transformation which preserves their normalization. Okay, that we call a unitary transformation. Okay, so the Schrödinger equation, which is the central equation in quantum mechanics, basically just says that an isolated quantum system evolves over time by means of some unitary matrix getting applied to the vector of amplitudes to produce a new vector of amplitudes. Okay, now this is already interesting if we talk about just one qubit in isolation. Okay, but if we had two qubits, the rules of quantum mechanics tell us very clearly that now we need 4 amplitudes. We need an amplitude for both qubits to be 0. We need an amplitude for 0, 1. That is, the first qubit is 0 and the second is 1. We need an amplitude for 1, 0, and we need an amplitude for 1, 1. Okay, if I have 3 qubits, then now I need 8 amplitudes. Okay, 1 for every possible 3-bit string. And in general, the number of amplitudes will double with each qubit that I add. Okay, and this has a staggering consequence, which was noticed from the very beginning of quantum mechanics. Schrödinger's paper 100 years ago, which is that you need an exponential number of parameters to keep track of even just a very small quantum system. Okay, if I have 1,000 qubits, now we're talking about 2 to the 1,000 power amplitudes, which is more than could be explicitly written down in the entire observable universe. Okay, now why do I need so many? Well, it's simply because, in general, the qubits need not be independent of each other. Okay, they could be in what we call an entangled state, where, measuring one qubit tells you something about the states of the other qubits. Okay, and so just like, to specify a probability distribution over n-bit strings, I would need 2 to the n real numbers. Okay, in the same way, to specify a superposition over n qubits, I need 2 to the n complex numbers. Okay, but the difference is that with a probability distribution, you could always just choose to say, if you wanted, that the exponentiality is only in your head, right? That really each bit is either a 0 or a 1. You just don't know which it is, and so you represent your imperfect knowledge of the situation using these probabilities. But as soon as you look, you'll see that it's really one or the other. With qubits, we don't really have that luxury, okay? Because of the potential for interference between the different amplitudes. Okay, so the amplitude, there has to be something about the amplitudes that is sort of out there in the world, that is not just in our heads. Okay, and now we're saying that there could be an exponential number of these things that are somehow out there in the world. Okay, and so that's an absolutely staggering claim about reality. In fact, to a computer scientist, this might be, the most staggering fact about quantum mechanics. Okay, that just to keep track of the states of, let's say, 1,000 little particles, nature off to the side somewhere has to keep track of 2 to the 1,000 parameters. And anytime something happens to the particles, nature needs to cross off those 2 to the 1,000 parameters and replace them with new parameters. Okay, that's a staggering amount of work for nature to be going to keep track of these particles. Okay, chemists and physicists, realized this generations ago. They realized it mostly as a practical problem. Okay, that if you're trying to simulate quantum mechanics on conventional computers, for example, because you want to understand the energy levels of a complicated atom, you want to know the rate of a chemical reaction, you want to know whether a certain material will be superconducting or not, or will be useful as a battery, right? These are all many-body quantum mechanics problems, okay, that involve keeping track of very complicated entangled states. And even today, they push supercomputers to the limits to do these kinds of calculations, in large part because of the exponentiality of the quantum state. Okay, and so it was all the more so in the 50s and 60s. But it was not until the 1980s that a few physicists, most famously Richard Feynman and David Deutsch, started saying, well, if nature is giving us this computational lemon, why don't we make lemonade out of it? In other words, why don't we build computers that themselves would be made out of qubits, that themselves would be able to take advantage of this exponentiality of the amplitudes and of entanglement and interference. Okay. Now, of course, they then faced the question, supposing that you built that device, what they called a quantum computer, what would it be good for? Okay, so we'll talk a lot about that question today. Okay, but at the time, they mostly just had one answer to that, which is it would be good for simulating quantum mechanics itself. Okay, and you could say in the 40 years since then, we have struggled with only some successes to improve upon that answer. Okay, now at this point, I can directly address sort of the central misconception about quantum computers that you will see in, unfortunately, in just about every popular article that gets written about this subject, and even scientists in adjacent fields have often fall for this. Okay, what people want to say is that, well, a quantum computer is just a massively parallel computer that just speeds up pretty much everything by trying every possible answer in parallel. Okay, so they say a conventional computer, is built out of bits that have to be either 0 or 1, and therefore it has to try every possible solution one after the next. But because a quantum computer is built out of qubits, which can be in superposition states, therefore a quantum computer can just try every possible solution at once, each one in a different parallel universe, if you like. Okay, and then it's typically implied, without saying so, that somehow you can just magically pick which solution is the correct one. And if that was how it worked, then that would indeed be incredibly useful. Anyone could see that, right? It could break any cryptographic code, solve any optimization problem in just an instant. Unfortunately, that is not how it works. Okay, and we're now in a position to understand why. Okay, it's true that with a quantum computer, you can create a superposition over all the possible answers to your problem, even if there are exponentially many of them. Okay, that's even an easy thing to do with a quantum computer. Okay, you just put each of your, say 1,000 qubits into an equal superposition of 0 and 1. Okay, now boom, you have an equal superposition over all 2 to the 1,000 strings of 1,000 bits. Okay? The trouble is that for a computer to be useful, at some point you have to look at it. You have to measure, you have to get an output. Okay? And if you just measured an equal superposition over all possible answers, not having done anything else, then the rules of quantum mechanics are very clear that what you're going to see is just a uniformly random answer. Okay? Just a random 1,000-bit string. And well, if you just wanted a random 1,000-bit string, you could have just flipped a coin 1,000 times, right? You didn't need to spend all these billions of dollars, presumably, to go, build this quantum computer. Okay, so for this reason, the only hope of getting any advantage from a quantum computer is to use the way that amplitudes, being complex numbers, work differently from conventional probabilities, which are non-negative real numbers. Okay, so with every algorithm for a quantum computer, the basic game that we're playing is to choreograph a pattern of interference such that for each wrong answer, each answer that we don't want, some of the contributions to its amplitude are positive and others are negative. So on the whole, they cancel each other out. Whereas for the right answer, the answer we do want, we want all the different contributions to its amplitude to be pointing in the same direction. Okay? If we can arrange that, then when we measure, we will see the right answer with a large probability. Okay? And if we don't see it, we can keep repeating the computation several times until we do. Okay? But we want to boost the probability of seeing the right answer to be much, much larger than it could be, using any classical process that would run for any similar amount of time. Okay, that's one of the very hard parts. Okay, you always for this to be useful, you have to compare against the best classical algorithm that there is. Right? And classical algorithms get to fight back. Okay? Meaning, just because you can't think of a fast classical solution doesn't mean that someone else won't think of one in the future. Right? And if they do, then maybe you don't need the quantum computer anymore. Okay? So that's one, very, very hard thing here. Okay? The other very hard thing is that you have to somehow concentrate all the amplitude, onto the right answer, even though you yourself don't know in advance which answer is the right one. Because if you already knew, what would be the point? Right? So you need to just arrange this computation with some mathematical guarantee that the interference is going to happen constructively on whichever answer turns out to be the right one. Okay? Nature here is giving us an ability that is weirder than any science fiction writer would have had the imagination to invent. It's giving us this completely bizarre hammer, and then it's our job as quantum algorithms researchers to figure out, which nails can that hammer hit? What is this good for? Okay, so without further ado, what are the main applications that are known for quantum computers? After 35 years of researching that subject. Okay, so we do have an interesting list of applications. I think it is shorter than many people would like it to be, but it's certainly not empty. Here I think is sort of the honest list of the main things that a quantum computer is good for, and and this picture, like, I could have used this slide. I could have put most of what's on this slide 25 years ago. Okay, the list has been fairly stable, even as our knowledge of the details of each of these application categories has advanced. The basic categories themselves are still the ones that we knew in the 1990s. Okay, so first of all, there is the application discovered 30 years ago by Peter Shor. Okay, this was sort of the one that brought quantum computing to the attention of most of the world. Okay, when Shor discovered that if you were to build a scalable quantum computer, meaning that worked reliably with millions of qubits and billions of operations on those qubits, then you could use that to quickly find the prime factors of huge positive integers. Okay. Now, why do we care about that? Well, it so happened almost all of the public key encryption that protects the internet is based on codes whose security depends on the belief that factoring is a hard problem, or that a few closely related problems are hard. Okay, if you what Shor showed was that if you could build a quantum computer, then you could solve these problems in number theory efficiently that modern cryptography requires to be hard. Okay, such as factoring, discrete logarithms, some elliptic curve problems. Okay, and you could thereby break HTTPS, steal people's credit card numbers. You could steal probably at least $100 billion worth of Bitcoin, including Satoshi's original Bitcoins, which are protected by only using elliptic curve cryptography. Okay, and so this would be a huge headache for the world. So this made many people interested in quantum computing who wouldn't otherwise have been, like the national security and intelligence communities. Now, it's not obvious that that breaking all these crypto systems would actually be a positive for humanity. Mostly it would be it would be a positive for whatever spy agency or criminal syndicate had the ability, for at least for as long as other people didn't realize that they had it. And it would be a huge headache that once everyone realizes this, if not sooner, then we all need to upgrade to quantum resistant methods of encryption. And actually that project is already underway. Okay, the U.S. federal government, companies like Google, have already started migrating to quantum-resistant forms of encryption. With the hope of completing that transition within the next decade. Okay, so. If that's successful, then you could say we'll all just be back where we started. Okay. In any case, actually demonstrating this will almost certainly require a fully error-corrected quantum computer, which is not a kind that we have yet. although that might actually be coming sooner than many of us expected. Okay, so now it's crucial to understand that in order to develop his algorithm, Shor needed to exploit very, very special structure in problems like factoring. Okay, so it's that structure that comes from abelian groups, period finding, things like that. That structure is what made factoring so useful for public key encryption. Okay, but it was a double-edged sword. Okay, that the same structure is what Shor was able to exploit to find a quantum algorithm that, using a Fourier transform, was able to just sort of concentrate amplitude onto an outcome that reveals the factors of your number. Okay, it doesn't work, even for breaking arbitrary public key cryptographic codes. Okay, let alone for solving arbitrary search problems. Okay, so then that brings us to what could a quantum computer do that is actually useful outside of code breaking. Okay, and then we can come back to the original application of simulating quantum in physics and chemistry themselves. I happen to think that is still 45 years later the economically most important one that we know. Okay, this could be useful for the photovoltaics industry, the battery industry, for high temperature superconductors, for designing industrial processes like maybe new ways to make fertilizer, could be useful for biochemistry, conceivably. Okay, and better yet, there is some hope that we'll be able to do useful quantum simulations even before we have fully error-corrected quantum computers. Okay, we're already starting to do some interesting simulations of condensed matter physics, and maybe we'll be able to do commercially useful quantum simulations within the next few years. Okay, and then there is everything else. Okay, so there's all the workhorse problems of computer science, like machine learning, optimization, combinatorial search. Okay, and so scheduling flights for an airline, right, or finding optimal parameters for an ML model like a neural net. Okay, and within the last 20 years, a narrative took hold that this is going to be, the great application of quantum computers, that they're going to speed up all of that. Okay, but I think the reality in quantum algorithms research is that, for these types of problems, the quantum speedups that we know are either relatively modest or else they're relatively specialized. Okay, so since 1996, we've known of a quantum algorithm called Grover's algorithm. Okay, and this is Love Grover over here, and that's the second most important quantum algorithm after Shor's. Okay, and it is able to search any list of n possible solutions for a good solution, assuming that you know how to recognize one when shown it, using a number of steps that grows only like the square root of n. Okay, so that's a quadratic speedup, a square root speedup. Okay, so compared to Shor's algorithm, Grover's algorithm has an enormously wider range of applications. Okay, so it's not just for number theory problems. It's for more than half of everything in an algorithm's textbook has some component that involves just searching through an unordered list of items for a good one, and that could therefore be Groverized. Okay, but the disadvantage of Grover's algorithm is that the speedup is only a square root. Okay? Now you might say a square root speedup sounds pretty good, right? It's better than nothing. I'll take it. Okay, now practical difficulty is that running an error-corrected quantum computer at all, which Grover's algorithm will require, will involve an enormous overhead. okay, optimistically, let's say by a factor of 1,000,000, okay, using the known error correction methods. Okay, and so now the question that you're asking is not about n versus square root of n, but rather n versus 1,000,000 times square root of n. Okay, where n is the size of your search problem, the number of solutions. Okay, and now eventually, if n is large enough, 1,000,000 times square root of n will become less than n, but that will only happen once n is in the trillions. Okay, so it's that issue that seems to put getting a win from Grover's algorithm compared to classical computers, much further into the future. Okay, and then if we don't have the Grover speedup, then we're left with the hope that some other quantum algorithm will be able to get a better than Grover speedup for optimization problems, NP-hard problems, machine learning problems, things like that. Okay, but after 30 years of research, I think the picture that's emerged is that, if there are better than Grover speedups, they're probably only for special types of optimization problems. Okay, ones with some kind of special structure, that would come from error correcting codes or from quantum walks on special types of graphs or things like that. And we don't actually know, how whether those optimization problems that admit exponential quantum speedups, will be useful in applications. We may not know that until we actually have large quantum computers and we can test some of these algorithms out, like this adiabatic algorithm or QAOA. There are a lot of quantum algorithms that have been proposed for optimization problems where I would say the case for them is mostly heuristic, right? It's that, well, you can try them out and maybe they'll perform better, but you have to now compare them also against the best classical heuristic optimization methods that we know, such as simulated annealing, for example, and it's not obvious in what cases the quantum algorithms are actually going to win. Okay, so there's this huge, murky zone in optimization and machine learning where, we're not going to really know the scope of quantum speedups until we can test this out on a large scale. Okay, now I like to say that for me, the single most important application, more important than optimization or than code breaking or even than quantum simulation, is just disproving all the people who said that quantum computing was impossible. Okay, or in other words, testing quantum mechanics itself in maybe the most severe way that we're ever going to test it. This is why I'm excited about building quantum computers, and I feel like if they will also be useful for various things, then that's just icing on the cake. Okay, but unfortunately, that's sometimes a harder case to make to the funding agencies. Okay, so here's a little picture of how we organize the different classes of problems in theoretical computer science. So we organize them into these classes, complexity classes, which consist of all the problems that are solvable within some various resource constraints. Okay, so our most famous classes are called P and NP. Okay, P stands for polynomial time, and it contains all the problems that are solvable on a conventional computer, like the one in your pocket. Okay, using a number of steps that grows only like the size of the input raised to some fixed power. So linear in n or quadratic, n squared, n cubed, where n is the number of bits of input. Okay, and P actually includes most of the problems that our computers are solving on a day-to-day basis, including all the basic arithmetic operations, searching maps like what Google Maps does, and even many very non-trivial examples like testing whether an integer is prime, or linear programming, maximum matching in graphs, things like that. Now, NP stands for non-deterministic polynomial time. Okay, it's not polynomial. Okay, it's non-deterministic polynomial. Okay, and NP is the class of all the problems for which there is an efficient algorithm, that is a polynomial time algorithm, to recognize a valid solution if you're given one. Okay, so so factoring, which we've talked about, is a very famous example of an NP problem. Okay, as far as we know, if I give you a huge composite number, like with thousands of digits, then using any classical algorithm, it might take you longer than the age of the universe to find the prime factors. Okay, it may, the fastest known factoring methods use time that is exponential, actually not in the number of digits, but in the cube root of the number of digits of the number that you're trying to factor. But nevertheless, if someone claimed to have factored a number, then it's very easy for them to prove that to you. They just have to show you the factors, and then you can check them for yourself. Okay, you can check that they're prime using fast primality methods, and you can multiply them together. Okay, so for that reason, the factoring problem is in NP. Okay, NP consists of all the problems for which solutions are efficiently checkable, even if they might take exponential time to find. Okay, now the most famous unsolved problem of theoretical computer science, one of the most famous unsolved problems in all of mathematics, is of course whether P and NP are equal. Okay, this is a problem where you get $1 million from the Clay Math Institute if you solve it. Okay, although actually if P were equal to NP, and you demonstrated that by an algorithm that was fast in practice, you could get much more than $1 million. You could, for example, get hundreds of billions of dollars by mining bitcoins. Okay, you could also program your computer to solve all the other famous unsolved math problems, like the Riemann hypothesis and Goldbach's conjecture and so forth. Okay, so P versus NP is an enormous problem. Almost all of us conjecture that P is not equal to NP. Okay, so that there are efficiently checkable problems that are not efficiently solvable. Okay, but that hasn't been proven. Now, the hardest problems in NP are called the NP complete problems. Okay, these are the problems that are NP complete, and where if you had a way to solve them, then you could efficiently solve all problems in NP. Okay, the great discovery of the early 1970s that really started theoretical computer science as in the modern sense, was the discovery that hundreds and hundreds of the problems that we care about in practice actually are NP complete. Okay, so you could have traveling salesmen, or finding large cliques in a graph, like highly connected subgraphs, or you have Boolean satisfiability, you have all sorts of other combinatorial search and optimization problems that a priori seem totally unrelated to each other. They might all be hard or easy for separate reasons. And the great discovery of NP completeness was that all these problems stand or fall together. Okay, either all of them are in P, all of them have efficient solutions, or else none of them do. And all of them basically require brute force search. Okay, now there are problems that are in NP and that are not known to be either in P or NP complete. Okay, so they're in this sort of no man's land in the middle. Okay, and factoring is a very famous example of such a problem. Okay, factoring has special structure that seems to prevent it from being NP complete, but we also don't know it to be in P. Okay, most of the problems that are useful for cryptography are in this intermediate zone, okay, between P and NP complete. Okay, and now we can talk about where does quantum computing fit in. So, so there's a quantum generalization of P, which is called BQP, bounded error quantum polynomial time. I drew it with a wavy border since, you know, everything quantum is spooky and weird. And what Shor showed was that BQP contains the factoring problem, which means that either BQP is strictly larger than P, you know, quantum computing must be more powerful than classical on at least some problems, or else factoring must be in P. Okay? One of those things has to be true. We can't prove unconditionally that BQP is larger than P. The reason why not is that all these classes, P, BQP, NP, are contained in another class called P space. And we can't even prove that P is not equal to P space. And if P and P space were equal, then all these classes would come crashing down to P. Okay, so you know, the idea that quantum computers will ever give us exponential speedups, you know, rests on unproven conjectures, but they do seem like very, very plausible conjectures. Okay, now in the other direction, we also so we don't know whether BQP contains NP. Okay, that's you know, as I said, for most of the NP complete problems, we only know how to get a Grover speedup, and not better than that. So you know, it would be a revolutionary development if BQP were to contain an NP complete problem, right? And if it contains one of them, then it must contain all of them. Okay, so that, you know, it seems like a plausible conjecture that just like P is not equal to NP, also BQP does not contain all of NP. Okay, so quantum speedups are, you know, do require special structure in your NP problem. Now, in the other direction, we also don't know whether BQP is contained in NP. So there might well be problems that quantum computers can efficiently solve, but for which a classical computer cannot even efficiently check the answer, let alone finding it. Okay, and simulating quantum systems itself seems like a very good candidate for that kind of problem, where, you know, it may be that for quantum simulation, the only way to check the quantum computer's answer will be using a second quantum computer, okay, or by comparing to, you know, the results of an experiment. Okay, and you know, this has already become a live issue in the quantum computing experiments that are being done right now. Okay, so so I mentioned that you know, a narrative took hold like 20 years ago that quantum computing is going to revolutionize AI and optimization. Okay, because, you know, everyone liked to hear that. You know, journalists liked it, investors liked it, you know, startup companies liked it. You know, the only problem is that you know, I think most of this is not actually supported by the quantum algorithms that we actually know. Okay, so with heuristic quantum algorithms for optimization, you know, they're you know, we don't really know like for what class of problems, you know, do they get speedups over the best classical algorithms, and is that a class of problems that matters in practice? Now, starting around 2008, there's been a lot of excitement about a different class of quantum algorithms for machine learning problems, which grew out of something called the HHL algorithm, or Haro-Hassidim-Lloyd algorithm. Okay, and these are algorithms that sort of can do linear algebra on exponentially large matrices, like, you know, inverting them, solving exponentially large linear systems, you know, in only polynomial time, right? Which sounds great, which sounds like that would be super useful for all sorts of machine learning tasks. Okay, but with these problems, there's a different catch, which is that these algorithms tend to like give you a solution that just that is never written down explicitly in any place where you can see it. Okay, so like they will solve your linear system, but the solution vector will not be written down in any memory that you can read. Instead, the solution vector will just be there implicitly as the set of amplitudes of a quantum state. Okay, and it will then be up to you to figure out a way to measure that quantum state in a way that actually tells you something useful about your machine learning problem. Okay, the quantum algorithm designers will say, their work is done at that point, right? And now you have to figure out how to measure this quantum state to tell you something interesting. And not only that, but you need to learn something interesting by measuring this state, and that you couldn't have learned by a fast classical algorithm. Okay, so that's the challenge here. It's been, there are what look like a lot of exponential speedups for sort of abstractly described problems, involving mapping some quantum states to other quantum states. But the challenge remains of turning these into an end-to-end speedup. That is a speedup, mapping classical input, like you might have in a real life, machine learning situation, into a classical output that you would actually want, and doing that faster than any classical algorithm could do the same. Okay, and what's crucial is that you have to do a fair comparison. People learned over the last 20 years that they can just make quantum computers look good by saying, we use the quantum computer to do such and such, recognize handwriting or route vehicles or whatever, and then just not bothering to compare to a classical solution at all. Or if they do, then comparing to only a brute force classical algorithm. Okay, but no, for this to be interesting, you need to compare against the best classical algorithm that anyone can find. Okay, and quantum is only useful if it still wins. Okay, so let me just give you a little story to tell you, the subtlety of looking for quantum speedups. Okay, so in 2016, there was a proposed quantum algorithm for a machine learning problem, which was called the Karanides-Prakash algorithm. Okay, and this was for recommending products to users in a recommendation system like Netflix. Okay, and I was impressed by this algorithm, right? Because it actually did deliver an end-to-end exponential speedup over the best classical algorithm that was known for the same task, and there were some assumptions about the data, about how the data was represented inside of a RAM, a memory that a quantum computer could access. Okay, but they were plausible assumptions, right? And so I had a really amazing 18-year-old undergraduate named Ewin Tang who was looking for a project to do. So I asked her, can you prove that this quantum speedup is real for the Karanides-Prakash problem? So in other words, could she prove that any classical algorithm for that same problem would require exponentially more accesses to memory than the quantum algorithm managed to make? Okay, like the quantum algorithm used only log of n accesses. We wanted to show that any classical algorithm would need at least n, or square root of n, or something like that. Okay, so this is a type of result that we sometimes can prove. And Ewin worked on this problem for about a year. Okay, she had many failed attempts on it. And then after a year, she said to me, I think I know why I haven't been able to prove this result. It's because it isn't true. Okay? It's because there is a classical algorithm that's only a little bit slower than the quantum algorithm. Now I was skeptical of that, but Ewin turned out to be right. Okay, and since then, building on what Ewin did, a whole bunch of other quantum algorithms for machine learning problems have now been dequantized. Okay, so they've been replaced by similarly efficient classical algorithms. Okay, and so this has been an amazing development intellectually, not so great for the field of quantum machine learning. Right, you now need to sort of build anew. Right, find some new types of problems where you can get an end-to-end exponential quantum speed up, or at any rate better than the Grover speed up, and where that speed up cannot be Ewinized, cannot be defeated using Ewin-like techniques running on a classical computer. Okay, so this underscores that this is not just a matter of dotting the I's and crossing the T's. This is not just a matter of theorists being theorists. This is a real issue. Okay, sometimes apparent quantum speedups go away because classical computers can solve the problems too. Okay, so for the past 5 or 6 years, I've been very, very interested in the quest to demonstrate any quantum speedups that we can, and just demonstrate them using currently existing hardware in a very clear way. And I don't really care if these speedups are useful for anything. Okay, I say, before we worry about useful quantum speedups, let's just establish as firmly as we possibly can that we have any quantum speedups. Okay, that we have quantum speedups, even just for completely contrived problems that where we really do beat classical computing, in a way that's going to stand the test of time. Okay, so some theoretical work that my student Alex Arkhipov and I did 15 years ago on a proposal called boson sampling helped to start this quest for what was later named quantum supremacy. Okay, so what Arkhipov and I suggested in 2011 was that even if you had just a very, very rudimentary type of quantum computer, where all you could do was generate a bunch of photons and then send them through a network of beam splitters, and then just measure where the photons ended up. This, we don't know if it would be useful for anything, but at any rate, it looks like simulating what that experiment does would already be classically hard. Okay, we were able to give theoretical evidence for that. Basically, if there were a fast classical algorithm that could sample from the same probability distribution that nature samples from, over all the possible locations where all your photons could end up, then this would have surprising consequences for classical complexity theory. If it was an exact simulation, then it would lead to what's called the collapse of the polynomial hierarchy, which would be almost as dramatic as P equaling NP, although not quite. If it were only a noisy or approximate simulation, then we think that it might have that consequence, but now we would need to make a further conjecture. Okay. At any rate, it would lead to classical algorithms way beyond any for well-known hard problems like estimating the permanence of n by n matrices that would go well beyond any of the classical algorithms that we currently know to exist. Okay, now boson sampling, was just a theoretical idea when we came up with it, but it's since been experimentally demonstrated with, most recently in the past year, something like 1,000 photons by the group of USTC in Hefei, China. Okay, and so they have very, very clearly beaten sort of any known classical algorithm, in terms of the probability distributions that they're able to sample from, using this kind of simple optical setup. Okay, but actually even before that had happened with boson sampling, there was a related approach called random circuit sampling that sort of got there first. Okay, and so there was a team at Google of John Martinez, starting in 2015, that said we want to build a quantum computer with superconducting qubits, and with at least like say 50 to 100 qubits, and we want to do something with it that will demonstrate superiority over a classical computer. And they looked around for what to do, and sort of the only thing you could do was something like boson sampling, except adapted to the setting of superconducting qubits. Okay, so that was something that we called random circuit sampling. Okay, and we worked with them. We then developed the theory of those random circuit sampling experiments, and Google actually demonstrated the first quantum supremacy experiment, based on random circuit sampling in 2019. Okay, and since then they've continued to improve it. Their original experiment can now be simulated quite easily by a classical computer. Okay, so you could say like their original claim, quantum supremacy claim did not stand. Okay, but by now they have much better quantum supremacy demonstrations with up to 100 qubits, where even using the best classical algorithms that anyone has come up with in like the past 6 years of trying to match these kinds of experiments, it looks like those algorithms running on the largest classical supercomputers that we have, could take 10 to the 25 years or something like that. I should mention that just a month ago, John Martinez was shared the Nobel Prize in Physics, although not for the quantum supremacy, for the earlier work that he did that laid the foundation for having superconducting qubits at all. Okay, so you could say the situation sounds pretty good in terms of demonstrating the reality of quantum advantage, even if so far it's just been for these fairly artificial sampling problems. Okay, but these sampling problems also have a huge drawback, which we understood from the beginning when we first proposed them. Okay, and that's that it is, for the same reasons why it seems very, very hard for a classical computer to simulate these experiments, it is also very hard for a classical computer to check the answer. Okay, so these quantum supremacy experiments are not solving NP problems like factoring, right? If you built a quantum computer that could run Shor's algorithm to factor a number, then it would be easy to convince any skeptic of what you had done. You could just say, give me a huge composite number, then I will give you its prime factors, and then you can check those yourself. Okay? With quantum supremacy experiments, the proof that they're working correctly is necessarily statistical. Okay? It's that you have to collect a bunch of outputs from running this experiment over and over, and then you have to do statistics on those outputs to check, are these consistent with being drawn from the probability distribution that I want. Okay, and the trouble with doing those statistics is that in order to calculate them, you need to do an exponentially long computation with your classical computer, okay, in order to calculate what the probabilities in question were supposed to be. Okay, so so the result of that is that like you can do these experiments with 50 qubits, and then checking them involves doing like 2 to the 50th arithmetic operations, you know, which the largest supercomputers in the world are able to do. And so that's exactly what people did to check the results. But if you do these experiments with, say, 100 qubits, then there's no way to directly prove that they work correctly. Okay, because even the largest supercomputers in the world can't do 2 to the 100 arithmetic operations, as would be needed to check the results. Okay, so you know, the way that I think about it is that, you know, in demonstrating a quantum speedup, we really want 3 properties. Okay, we first of all want something that we can actually implement using the hardware that exists today, or that, you know, will exist in the next couple of years. Okay, second of all, of course, we want a clear advantage over the best classical algorithms that exist for the same task. But then thirdly, we want there to be a fast way of checking the answer. Okay, you know, either, you know, using a classical computer, or, you know, using some sort of verification protocol. Okay, I would say that, you know, the situation for the past few years has been that we've known how to get any 2 of these 3 requirements. Okay, so the quantum supremacy experiments that we've been doing based on boson sampling or random circuit sampling, these you know, get a pretty clear quantum advantage, and we can do them today, but we can't verify the answers when, you know, after we've completely gone beyond the realm where a classical computer could simulate our experiment. Okay, you know, we also know, you know, things like Shor's algorithm that we know should get a very clear quantum advantage and be verifiable, but we can't implement them today. And then there are all these quantum algorithms, you know, like the heuristic ones for optimization problems that we can run on today's devices. They do have verifiable answers, but we don't really know if we're beating the best classical algorithms. Okay, so then the question is, how do we get into the intersection of all 3 circles in this diagram? Okay, now I'm delighted to report that even just within the last couple of months, there have been major announcements by several different groups who have candidates for getting into the center of this Venn diagram. That is, you know, a near-term, you know, efficiently verifiable quantum advantages. So the group at Google has announced recently a major experiment that they did to measure something called out-of-time order correlators, or OTOCs. Where they run a certain a random quantum circuit forwards and then backwards, you know, having done just a single gate in between. Okay, and then they look at the effect of that one gate on what happens as you reverse the time evolution of your circuit. And what they find is, well, if your quantum circuit was too small, then, you know, that this one gate wouldn't have much of an effect, because there just wouldn't be enough time for the effect to propagate. If your random quantum circuit was too large, then just changing one gate just totally scrambles up everything, and you get, you know, just a completely random output. But there seems to be an intermediate regime where, you know, you change this one gate and something interesting happens to the expectation value of some observable, but you can't calculate it, you know, or at least they don't know how to calculate it efficiently with a classical computer. You seem to need a quantum computer to estimate that observable. Okay, so now this is a case where we still don't know that the problem is in NP. Okay, so we don't know how to check the answer using a classical computer, but at least we could check the answer using a second quantum computer. Right? So, the quantum computer is not just returning samples from a probability distribution, it is estimating a specific number. Okay, and you could then run a second quantum computer, even like using different hardware, for example, and you could see whether it returns the same number or not. Okay, so as long as no one finds a fast classical way to simulate these OTOC experiments, then this looks like a very strong candidate for a more verifiable form of quantum supremacy. Okay, now a company called QubiTO has also announced a demonstration that they did on the trapped ion devices of Quantinuum. That involved obfuscated peaked quantum circuits. Okay, so peaked quantum circuits are a notion that my student and I defined a few years ago, where we said, suppose that you have a quantum circuit that looks completely random. To a classical computer, it looks like it's just completely scrambling things up and giving you a random, or a pseudo-random quantum state. Okay, but secretly, it's been chosen in just such a way that it will return a single classical output with a large probability. Okay, so the output distribution is peaked at a single classical string, okay, for some obfuscated reason. Okay, if you could design those kinds of circuits efficiently, then this would give you a path to a verifiable quantum advantage that would work on current hardware. Okay, and so now what QubiTO has done is that they have stuck their necks out, and they have given a candidate class of exactly this. They design these peaked quantum circuits, and then they do all sorts of things to try to obfuscate the peak, to scramble up the circuit and make it hard for a classical computer to examine that circuit and figure out where the peak was. Okay, but if you run the circuit on a quantum computer, then the peak just pops out of the output. Okay, so again, this actually would be an NP problem, right? This actually is a fully verifiable quantum supremacy, unless someone finds a fast way to reverse engineer these circuits with a classical computer. Okay, so that's now the challenge that they have thrown down to refute their claim by breaking it classically. Okay, there's also been an exciting theoretical proposal by Deshpande et al. For getting verifiable quantum advantage, almost as soon as you can do any sort of quantum error correction. Okay, and so I hope that someone will experimentally demonstrate that. Okay, now until recently, people said that these quantum supremacy experiments that we've been doing, for example, based on random circuit sampling, they might be interesting as a proof of principle, as a demonstration of how far the hardware has come, but they're clearly in and of themselves completely useless, right? We didn't design them to solve any useful problem, as I said, right? We just designed them to do something that is classically hard. Okay, but even that a statement might be challenged. Okay, so in a few years ago, my then postdoc Shihan Hung and I had a proposal for how to actually do something useful with the current type of quantum supremacy experiments. And that was to generate cryptographically certified random bits. Okay, so now just to be clear, if you want random bits and you trust your quantum mechanical hardware, then this is one of the easiest things that you could possibly ask for, right? You can just put qubits into equal superposition of 0 and 1 and then measure them over and over. And that will give you as many random bits as you like. Okay, you could even just put a Geiger counter next to some radioactive material and get as many random bits as you like that way. But now a much harder problem is, what if you need to prove to skeptics over the internet that these bits really are random? Okay, you did not you didn't do anything secret to make them deterministic, to make them predictable. Okay, and these skeptics don't trust your hardware. Okay, they don't even trust that you're using a quantum computer at all. Okay, so how can you prove to them that you really are generating random bits? Okay, so why would we care about this problem? Well, for example, proof of stake cryptocurrencies, like the current Ethereum, right? Since they did the merge, okay, depend on constantly running a lottery to decide who gets to add the next block to the blockchain. Okay, so so billions of dollars are riding on everyone trusting that these bits really are random, right? You get an enormous advantage in energy efficiency compared to the proof of work cryptocurrencies like Bitcoin. You don't have to use like 0.5% of all the world's electricity to invert a hash function. Okay, but you do need this certified randomness. Okay, and so what we realized was that these quantum supremacy experiments could almost immediately be repurposed to give you a scheme for generating certified randomness. Okay, and the way that it would work is that a classical challenger generates quantum circuits. Okay, they can generate these circuits pseudo-randomly. So they start with, let's say, a very small random seed. Okay, so you need a small initial investment of randomness here. Okay, but then using that small seed, you generate a quantum circuit in some pseudo-random way. Okay, you then send the circuit to the quantum computer, and you demand that it send you back quickly a bunch of samples from the output distribution of that quantum circuit. Okay, so the quantum computer has to run the circuit, a bunch of times, measure the output, send you back the result. Okay, now at your leisure, you can do the classical computations to verify that yes, these samples really are consistent with having been drawn from that distribution. Okay, that computation does take classical exponential time. So, that is a drawback of this scheme, and it limits us to doing it with at most, let's say, 50 or maybe 60 qubits. Okay, but if we do that, and if the quantum computer quickly sent back responses that passed the statistical test, then what we were able to show was that under some plausible cryptographic assumption, even a quantum computer could have only generated such samples quickly by sampling them from a distribution that has a lot of real entropy in it. Okay, it could not have done so in a secretly deterministic way. Okay, to do that, it would have needed to solve a problem that would have been hard even for a quantum computer. Okay, so this is well, it's the only thing that I've ever been involved in that has actually been patented. Okay, because it's maybe the only theory I've done that's in any danger of being useful. Okay, if someone wanted this, I think this could actually be the first realizable application of quantum computers that really does depend on them being quantum computers, right? You could not hope to do this using a classical computer, because using any classical method, you could always, substitute a pseudo-random generator, and no one would be able to tell the difference. Okay, whereas this is actually guaranteeing you genuine randomness under the computational assumption, and if the statistical test passes. So then, there was an interesting question: could anyone actually demonstrate this protocol? So I'm happy to say that just this year, in a collaboration with Quantinuum and with JP Morgan Chase, we actually demonstrated this certified randomness scheme to generate about 70,000 certified random bits using Quantinuum's trapped ion quantum computers. So it's not clear whether any cryptocurrency actually wants to use this. It's you need to be extremely paranoid to do things this way. And of course there are cheaper ways of generating randomness if you have if you're not paranoid about it in certain very specific ways. But I should mention that just this week, the Quantinuum and JP Morgan groups have published a substantially improved certified randomness generation, where now what they do is that they send the gates to the quantum computer one layer at a time. So they're just revealing the circuit to the quantum computer a single layer at a time. Okay, and so now they've made it that much harder for a classical spoofer, if there was one, to simulate the results, because that classical spoofer would presumably have to wait for the very last gates before knowing what to do, and it would then have to super duper rapidly swing into action. Okay, so I think that this is getting closer to actually being practically useful, but no one is using it yet. Okay, another exciting thing that we did with Quantinuum, and which was just announced a couple months ago, was that we demonstrated a different form of quantum advantage that we call quantum information supremacy. Okay, so here we did an experiment with 12 qubits where we could show that any description of the results of the experiment that was secretly classical would have required at least 60 classical bits to be passed from the earlier part of the experiment into the later part. Okay, more likely about 300 classical bits. Okay, so we get there's an exponential separation here between the number of classical bits that would have been needed and the number of qubits that we used. Okay, and what's new about this is that this type of separation does not depend on any unproved assumptions about problems being hard for classical computers. Okay, this we can just prove unconditionally that the separation is real. Okay, using results in what is called quantum communication complexity. Okay, but now this type of experiment is only feasible because of the kind of hardware that's become available over the last 2 years. Okay, specifically that we now can do 2-qubit operations that are about 99.9% accurate. Okay, and we really needed that because we really needed to do many hundreds of gates. Okay, so as I've already alluded to, there are a whole bunch of proposals that are being pursued at once for how to actually build a quantum computer. So there is trapped ions, often ytterbium or barium nuclei that are suspended in magnetic fields, manipulated using lasers. This is what Quantinuum is doing in Colorado. I've mentioned them several times. It's also what IonQ and Oxford Ionics and several others are doing. One can use cold atoms. There is a group at Harvard of Misha Lukin and a spin-off company called Quera that are the world leaders in that, I would say. One can try to build a quantum computer using photonics. Okay, this is what PsiQuantum in Palo Alto has been trying to do. Actually, there's also a leading group in Rome, in Italy, that has been doing this. And then, maybe the one that we've heard the most about lately has been superconducting qubits, which where you build a chip where currents can flow through coils in states that encode qubits if the chip is cooled to maybe like 10 millikelvin, so just a tiny fraction of a degree above absolute zero. So you build this chip and then you place it into a dilution refrigerator. Okay, and this is what Google has been doing, also IBM, also some startup companies such as Rigetti. Okay, and this is what a dilution refrigerator looks like down here. Okay, so a big advantage of superconducting qubits is that the operations are very fast, but a big disadvantage is that they're fixed in place, and each qubit can only interact with its nearest neighbors. This is in contrast to trapped ions or to cold atoms, where we can actually pick the qubits up and move them around to where they need to be. Okay, so a lot of people wonder, why is building a quantum computer so damned hard, right? The central reason for that is what we call decoherence, which means unwanted interaction between the quantum computer and its environment, which has the effect of prematurely measuring the quantum computer's state, right? It doesn't have, as I said before, it doesn't have to be a person who looks. Okay, any kind of unwanted interaction between a quantum computer and its environment can have this effect. The problem is so serious that there were distinguished computer scientists and physicists 30 years ago who said you will never be able to build a quantum computer at any significant scale. Right, maybe a tiny one, but as you make it larger and larger, decoherence will take over, right? You will never be able to protect all your qubits from being measured by the environment. And as the computation gets bigger and bigger, there will be more and more sources of error, and it will be more and more certain that some errors will happen somewhere, and then they will just ruin the whole thing. Now, in the view of most quantum computing researchers, what changed the whole story was the discovery of quantum fault tolerance in the mid-1990s. So basically, people discovered that you don't have to get the rate of decoherence all the way down to zero. Okay, you merely need to make it very, very small. And once it becomes small enough, then there are very, very clever quantum generalizations of error-correcting codes that can take you the rest of the way. Okay, you can constantly make measurements to see, like, has an error happened, and if so, what do we need to do to fix it? Okay, and crucially, these measurements will not tell you the quantum information that you care about. Like, is your logical qubit a 0 or a 1? They will only tell you information about errors. Okay, so you can be monitoring only to correct the errors while preserving the actual quantum states that you care about. Okay, now the trouble is that to get over the threshold where this fault tolerance becomes a net win, you need very, very precise physical control over your qubits. So you probably want 2 qubit operations with somewhere around 99.99% accuracy. Okay. The good news is that this past year, we have now clearly exceeded 99.9% accuracy. Okay. When I entered this field 25 years ago, it would have been amazing to have 50% accuracy. Okay. And then that 50% became 90%, became 99%. It's only within the last year that we have 3 nines. Okay, 3 nines should already be enough for error correction. If you're willing to do it in an expensive way, right? And if you have 4 nines, then you can even do it in a cheap way. Okay, so we're really, really getting extremely close to what is needed for a fault-tolerant device. And indeed, within the last year, we have seen the first experimental demonstrations from Google and others of actually encoding a qubit using an error-correcting code and preserving it, in a way where you preserve it longer and longer, the larger the error-correcting code you use. Okay, so let me summarize. I think that this is a really exciting time for quantum computing. After decades of theory and experiment, we are finally starting to see clear speed-ups over classical computers, at least for specialized problems. even some verifiable problems now with devices with up to 100 or so qubits, and we're even seeing now the beginnings of quantum error correction. Achieving full scalability and fault tolerance, and running Shor's algorithm to threaten public key cryptography, of course that will take longer. Okay, but what we've also seen is that even once you have a perfect quantum computer, right, it is a weird new resource. Okay, actually exploiting it to get a speed up over a classical computer is a subtle thing to ask for, and it heavily depends on exploiting the particular structure in the problem that you're trying to solve. Such as, for example, the periodic structure that you get in number theory problems like factoring. Okay, so this is not just free exponential parallelism. It's a weirder resource than any science fiction writer would have had the imagination to invent. All right, so thanks for listening, and I'm very happy to take questions.
Okay, so thank you very much. I hope you heard the round of applause. And we are sorry that we couldn't show the room, but due to privacy issues, it was not possible. Okay. But I can guarantee that besides the like 40, 50 people at home, there are like nearly 100, maybe more people here. And so thank you again for your lecture. It was really an interesting point of view on quantum computing and quantum advantage. Also for like the broad audience that we have here, because there are people mainly from computer engineering or maybe quantum engineering, but also people from other fields. So it was really great. Thank you.
Yeah, well, thank you for listening.
I mean, if you have maybe we have time for one or two questions. Of course, if you have time, Professor, for one or two questions.
Yeah, sure.
Okay, somebody has question? Okay. Sí.
First of all, thank you, Professor, for your nice presentation. I wanted to ask, despite like the initial development of the algorithm of quantum computing in the 90s, we have saw, as you said, a stagnation in the algorithm fields, and on the other hand, we saw classical approaches catching up, like tensor algorithm, or maybe quantum inspired algorithm and such. Also, we've seen the birth of analog quantum computers. So we saw moving from also digital to analog quantum computing to solve problem in physics to simulate materials and stuff. So I wanted to ask you an opinion about if this is due to the fact that thinking a quantum algorithm is inherently more difficult in respect to a classical one, and so is quantum, the theoretical part of the quantum algorithm is yet to come in the future, or just for you because the quantum part is not as powerful as we thought in the beginning?
Okay, so first of all, like everything is relative to your expectations, right? Like I don't think that we have a right to assume, to like demand of nature that quantum speedups would be useful for anything, right? Other than just simulating quantum mechanics itself, maybe, right? And so then, Shor's algorithm was a sort of miracle. Right, that this purely classical problem just happened to have the exact right structure for quantum interference to exploit. Right, so that was a miraculous discovery. Okay, now the trouble was, after that discovery was announced, then it was sort of like the story of Rumpelstiltskin, right? Or like, if you can spin this straw into gold, why not more and more and more, right? People just started expecting that now there will be quantum algorithms for everything, right? Even if that's not really true. Okay, so. I don't think that the issue is that it's so, is that it's so like uniquely hard to think about quantum algorithms. I mean, it's true that, we've had to learn a new way of thinking, right? To do quantum algorithms research. Think about quantum Fourier transforms and amplitude amplification and all these things. Okay, but a lot of classical algorithms are also really, really hard to think of. Right? They're also, really weird and counterintuitive. Okay, so it's not like that's a unique feature of quantum algorithms, right? I think, from a certain point of view, to a theoretical computer scientist, quantum computing is just another model of computation, right? It just, has some new rules involving unitary transformations and so forth, but, you can learn those rules like you learn any other rules. Right, I think that the heart of the matter is just that, a quantum computer, like I said in this talk, a quantum computer does not work by just trying, magically zeroing in on the needle in the exponentially large haystack, right? It's constrained by, first of all, the linearity of quantum mechanics. The fact that you can only do these linear norm preserving transformations to the amplitudes, and second of all, the extremely limited nature of quantum measurement. Okay, that when you measure, you just get a single sample with a probability that goes according to the amplitude squared. Right, and so what these things have told us from the very beginning, and I think that this was already clear to people who were paying attention like 30 years ago, right, is that you're only going to see a quantum speed up when you can choreograph this very, very special effect of interference, right, of that just happens, that to cancel out the contributions to the amplitude of each wrong answer and reinforce the contributions to the amplitude of the right answer. Okay, and now you could hope that would be applicable to some huge range of problems that we care about classically, but that was never more than a hope, right? There was never really anything to justify that. And so I think, we have continued to find new quantum algorithms. We haven't found anything quite as dramatic as Shor's and Grover's algorithms, arguably, right? There was low-hanging fruit that just got picked very, very early on. I think that we can be proud of the progress that we've made in sort of understanding at a much deeper level. Like what are the possible types of speed ups that you can get or not get for huge classes of problems that people care about. I think we do have a very good understanding, and it's just that understanding is that yes, this choreographing interference is a very special thing, as people could have known 30 years ago if they weren't deluding themselves about it.
There are another question. We have the last one.
Mm-hmm.
Okay.
Hello, Professor. Thank you for your talk. I wanted to ask you a question about why, I mean, maybe you have some insight or something about why there seems to be this boundary between NP and P class. Like, why are all of the important problems, for example, the protein folding problem and all of the other problems which fall in the NP category have to be separate from the P category? Like, do you have some... Is there some kind of a logical explanation to make sense of the fact that these important problems, they cannot be solved, have not been solved yet using polynomial? Yes.
Yeah, okay. Well, for P to not equal NP, I would say like that is the unsurprising possibility, right? That is like that is the thing that like if true, I mean of course we hope to have a mathematical proof of it someday, but I don't think that it requires any special explanation, right? All it requires is that yes, there are problems where checking a solution is easier than finding it. Okay, but that would be perfectly in accord with everyday experience, right? When you do a Sudoku puzzle, when you do a jigsaw puzzle, right? Like of course you expect that checking the answer will be a lot easier than finding the answer. Why? Because well, when you don't know the answer, then there's just a huge branching tree of possibilities that you need to try, right? And so when we conjecture that P is not equal to NP, all we are saying is that there are problems where that kind of brute force search will in fact be required, right? It's enough that there exist any such problems, in NP. Okay. Now it was a big discovery that that lots and lots of the problems that we care about are actually NP complete. Okay, which means that if you merely prove that P is not equal to NP, then each of those specific problems has to be hard, right? And that's a more interesting fact. Like that really does require more explanation, right? And in that case, when you go through the proofs of NP completeness, what you see is that like each of these problems has instances that sort of encode, the full difficulty of just sort of running a computer program, like running a Turing machine to verify some arbitrary output for some arbitrary NP problem. Okay, so that was a more interesting fact that like all these different problems are NP complete. Okay, but we have to add to that like in practice, like for a problem to be NP complete, all that it means is that there are hard cases of that problem that can be constructed. Okay, it doesn't mean that the cases that you care about that will arise in your application are going to be hard. And you mentioned protein folding, right? We've seen that very, very concretely with protein folding. Like within the last few years, AlphaFold, has, by some definitions, basically solved protein folding. Okay, it has made this enormous advance, which was awarded with the Nobel Prize in Chemistry. That it doesn't solve the problem in complete generality, but nature itself probably doesn't solve the problem in complete generality, right? There are proteins that you could engineer that would presumably take exponential time to reach their lowest energy folding configuration. Okay, just those are not very relevant for practice, right? For the proteins that are relevant for practice, there is we've already had these enormous advances, and there's plenty of hope that we could have more. And I would say the same for other NP complete problems, right? Yes, if, as I believe, P is not equal to NP, then there will exist hard cases of those problems. But there will also be many, many instances of these problems, that have some structure that can be picked off, either by a classical algorithm or perhaps by a quantum algorithm.
Okay, thank you.
Yeah.
Can I maybe ask a small follow-up?
Okay.
Do you think it is possible to invent arbitrarily powerful computing machines which are even more powerful than quantum computers, even though not physically possible to realize them?
Okay, yeah, that's something that I've thought about a lot. So certainly, mathematically, you can define computing machines that are as powerful as you want them to be, right? You could say, I'm going to define a machine with an oracle that will just solve the halting problem, or solve some arbitrarily hard problem within a single time step, right? Mathematically, that is easy to define. Okay, but now in terms of what can actually be realized in the physical world, I think that it is it's a plausible hypothesis, consistent with everything that we know today, that quantum computing is the end of the line, right? That in other words, anything that can be done efficiently by any physical machine could also be done efficiently by a quantum computer. Okay. Now, I don't know whether that's true or not. Okay, that belief is called the quantum extended Church-Turing thesis. Okay, so I don't know whether that's true or false. I would very much like to know. Okay, if there is, if you're looking for a counterexample to the quantum extended Church-Turing thesis, then you seem to be forced to think about possibilities that go beyond any currently known physics. So things involving like black holes or wormholes or closed time-like curves, or, in general, like quantum gravity. Quantum gravity is the main area of physics where we don't yet know, what the underlying laws should even look like. And so you can always speculate, that once we know quantum gravity, that it will do, just about anything you want it to do, right? And in particular, you could speculate that maybe quantum gravity would lead to some kind of physical computer that would go even beyond the quantum computer. But I wouldn't say that we have good evidence for that. So that's a very big question.
All right. So thank you all for your questions. And to wrap this up, I would say I want to thank you again, Professor Aaronson. I must say that we as students now have lived in this quantum realm and world for the best part of 2 years. And I must say it's very dark around us. It's very trippy. And it's very hard to find a good panoramic view of the world around us. And your talk surely helps shedding some light, at least of what's around us, which is a great start. I guess that what's in front of us will be something we have to find out.
Well, thank you. I'm very glad if it did.
And surely we'll keep reading your blog with great interest.
And best wishes to all of you with your studies and your work. Yeah.
Thank you very much, Professor. Thank you for your time and disponibility.
Great. All right, great.
Have a great day then, I guess.
Thanks a lot, and have a good evening. Okay, bye.